Okay, so we are going to have our last session of the school. Julio will give his third and fourth lecture.
Okay, thanks a lot, Sangmin. Hi, everyone. So let's keep going. Hopefully, we'll be as interactive as yesterday. I had a lot of fun, had many great questions, and also lots of great discussions after and also today. So please keep them coming. So let's start by recapping what I discussed yesterday. So as you'll see, the plan has changed a bit because I've been going much slower than expected. So I'm not sure I will have much time to discuss observables, but I will kind of deliver on the promise of teaching you how things are connected to self-force and how to expand in velocity. But I also wanted to go in a bit more detail about this exponentiation, since I kind of just mentioned it very briefly at the end of last lecture. But let's just recap what I explained yesterday. So we're focusing now on this classical limit of gravitational amplitudes. So what did that mean? It meant that we had Q over M being small. So what was Q? So we had this amplitude of a pair of particles with momenta P1, P2, and then the outgoing momenta were P4, which is minus P1 plus Q, and P3, which is minus P2 minus Q. So Q is the momentum transfer. And that divided by the masses of the particles was going to be very small. And also we had another small parameter, which was GMQ. And Q, of course, is the same as 1 over R or 1 over B. So this is just the weak field expansion. This was weak field. And this, I said that this was kind of classical versus quantum. Okay, but notice that this is also a large mass expansion. Okay, so this is just saying that the mass of the particles is very large relative to the momentum transfer. So today I will explain that this is useful when we are trying to understand the dependence of the amplitudes on masses. Okay, because when we are expanding at small q, we're also keeping track of various powers of the masses. Okay, and okay, just a comment, which might be useful later. In the dimensions, right? So this is slightly different because GM is actually the Schwarzschild radius to d minus 2. So, sorry, d minus 3. So the right expansion parameter is GM q to the d minus 3. Okay, in general dimension. Okay, and this classical limit, we were focusing on the regime where this Born amplitude was large. So we sort of had to exponentiate it, right? So we had to say that the amplitude, in order to, for instance, keep unitarity, the amplitude needed to go as e to the I times some classical object. And then that classical object, right, or in general is just some action. I'll also mention in more detail what this is. But this has some expansion into kind of a classical part and quantum corrections. And then the classical part itself has this expansion in GMQ. So it has like maybe like a free propagation part, 1 p.m., 2 p.m., etc., etc., which we'll review in a second, how they appear. And there were two main difficulties with this, which is that the thing that we really care about is this exponent here, but we know how to compute is the amplitude. Okay, and if you expand this exponent, there's going to be cross terms. For instance, there can be order h bar terms that hit terms that here go like 1 over h bar that come from the purely classical part. So there's going to be mix up between like quantum and classical things. And also the classical dynamics generically was encoded into subleading terms in the amplitude, right? So the leading term in the amplitude was just some higher power of something that came from lower orders. So we had this example of the box, that the leading term was kind of the square of something else, which I'll cover in more detail. Yeah. Okay, So let's look at examples, right? So yesterday we looked at this amplitude, this Born amplitude. So how did this scale? This scale like gm1 m2 squared over q squared. So this is basically this 1 p.m. thing, because this is the leading term. So if I expand this exponential at leading order, the amplitude is the same as the phase, perturbatively. Okay. What about at the next order? So for instance, we had this box diagram. So how did this go? So we had this term here, gm1 squared m2 squared. And then we saw that the leading term in the expansion of this box was something that went like gm1 m2. So this was something that naively was not surprised by GMQ, so it was not some PM correction, right? We're looking for things which have powers of this. And then at the next order, there could be a piece that goes like GM1 plus M2. So I can do a Q over M1 or Q over M2, right? So this thing gives me a 1 over Q. So indeed, this piece here is something like 2 p.m. and this is something like 1 p.m. squared. I'll explain this again in more detail. And there was also, in principle, some quantum correction. We looked at it for the triangle, but in principle, there can be a piece here that just goes like G log Q. So again, it's suppressed by Q over M compared to this, sorry, Q squared log Q. And this would be part of this S quantum. This would be the leading quantum correction over here. And this gets worse. So if we look at the next order, okay, just to show you. So again, now there will be something which is even more leading. Here I have G M1 Okay, so what is this? This is the leading order cubed. Okay, this is something like the leading order times the subleading order. So 1 p.m. times 2 p.m. and the actual new correction, which tells you new information, we need to go to subleading order in the soft expansion. Okay, so here, this would be literally the piece that gives me new information about the next perturbative order. Okay, so this is kind of inconvenient because, and it's just the fact that there's this exponential relation between the amplitude and really the classical quantity, which is the log of the amplitude. Okay, are there any questions about this? So more generally, if we had at odd loop orders, the classical correction will go q to the L minus 2. And if we are at even loop orders, it will go something like q squared to the L over 2. L minus 1 over 2 times log q. So we are always looking for a non-analytic piece of the amplitude, which is long distance, remember? And but it can come with powers of q in front. And you can check that the Fourier transform of these things are always powers of 1 over r or powers of 1 over b with the corresponding powers of g. Okay, and there were also more complicated things. So for instance, here at one loop, we could also have this loop of graviton. So I left as an exercise to compute how this scales. So let me just tell you the answer. So this thing will scale like just gm squared, m1 squared, m2 squared log q. So indeed, it's some quantum correction, because it scales precisely like this term here. And there's complications also at two loops, because in addition to this, I could have, for instance, this sort of diagram, right? So this thing is suppressed by h bar because it comes from like some quantum correction. So this is part of this as quantum. But now it's hitting tree-level Born amplitude. So if you power count this, naively, this has the right power counting. So this will go like, okay, so let's use the counting rules that we derived last time, right? So a leading order, each vertex gave me a power of the mass. So here I have g cubed, n1 to the fourth, n2 to the fourth. Then I have 1, 2, 3, 4, 5 graviton propagators. This is e squared to the 5. I have two loops, q to the 8, two vertices, q to the 4th. And then I have these two matter propagators that give me 1 over m1 q, 1 over m2 q. So this scales like g cubed, m1 cubed, m2 cubed, and all the powers of q cancels, but there will be a log left. So this looks like something classical, but one has to be careful because this is indeed kind of the overlap between a quantum term and a classical term. So this is suppressed by h bar, but this has a 1 over h bar. Okay, so this, we need to be careful because it's not really a quantum correction, and indeed when we take the logarithm, we would identify that it's not a classical correction. So we've identified that this is not classical. Okay, any questions about this? Yeah. So I will tell you two ways. One is just to compute the logarithm of the amplitude. And I will give you an example at two loop, but in principle, you can do that at high orders. And you would see that indeed you would have this piece, but in the logarithm, this piece would cancel. So you would see that in the exponent, this doesn't give you a new classical correction. Okay. The other way, so when I discuss how to use kind of velocity scaling, so we're going to identify like various regions also that contribute to various effects, like conservative, dissipative effects. And this velocity scaling is actually also very useful to tag what is a genuine like classical correction and what is something which is quantum. So for instance, we would say that as soon as we identify the classical regions, this diagram, if you just look at the regions that matter for the classical dynamics, automatically is 0. So you don't even need to worry about it once you start thinking about the velocity. Yeah. Okay, more questions? Okay, so let me tell you a little bit more about this exponentiation in case, here I'm just writing things like S1pm squared, S1pm cubed, but how do I actually see this in practice when I'm doing the calculation? So let's go back to the example of the box. Okay, well, first of all, let's remind ourselves about the scaling. So just what I told you yesterday. So when we take the tree-level diagram and we do the Fourier transform, okay, there was this Jacobian, and we do the 2D Fourier transform in the transverse space to P1 and P2. So this is something like Q dot B. Remember there were these delta functions times this diagram. In 4D, this gives me, or in general D, this gives me G, M1, M2. over B d minus 4, which in 4D is G M1 M2 log of B. Okay, and we also looked at the leading term in the box diagram. So let's look at this now. So what did the leading term in the box diagram look like? Okay, so when we did the power counting, okay, let's do it again quickly. So we have the measure, and then we have 2 propagators and 2 linear propagators. Okay, and let's do the counting in the dimensions, right? So this is going to give me, and I also have the masses. So this is M1 to the 4th into 2 to the 4th because of these 4 vertices. So what does this give me? This gives me M1 cubed, M2 cubed, Q to the D minus 4. Okay, because I have the measure here, but then I have, sorry, D minus 6. So I have 6 powers of Q because L scales like Q, and then I have the measure. Right? Sorry. This is wrong. Yeah. Thanks. No, the D minus 2 is because, remember when I wrote the Fourier transform of the amplitude, there were these delta functions that kept the on-shell condition in the external leg. So there was a delta P1.Q, 2P2.Q. So indeed, you're restricted on a plane in 4 dimensions, but it was because of this restriction. So here I already got rid of those. That's why I wrote the D minus 2. Yeah. Okay, but if this thing scales like, okay, so this is D minus 2. If this thing scales like Q to the D minus 6, right? And then we saw how many powers of M we had there. So indeed, we see that the leading term here is going to go like GM1 M2 squared, because the Jacobian cancels the extra powers there. And then we have D minus 6 and D minus 2. So this is the same as B to 2 times D minus 4. Okay, and we see that this scales precisely like the square of this leading term. Okay, and at subleading order, we will have 1 fewer power of B, which now would be a classical correction. Okay, so indeed, I did in D dimensions because it's easier to see these extra factors of B, but you see that the Fourier transform of the leading term scales precisely like the square of the tree. Okay, can we see this more directly in momentum space without doing the Fourier transform? Yeah, so. Well, we have to play some trick. So first of all, let me just point out that if I take the on-shell condition for, say, P3, which is this kind of the outgoing momentum, which was P2, here's my momentum conservation. This is the same as P2 minus Q squared, which is minus 2P2 dot Q. Right, so this tells me that actually P2 dot Q scales like Q squared. In fact, it's equal to Q squared. Okay, so this is actually suppressed in small q. Okay, so now let me look at the sum over the box and this cross box integral, because there will be something funny that happens. So what does this look like? I have the loop momentum. So let me put here L. Okay, so this propagator, and this propagator are identical in these 2 diagrams. And just have L squared sorry, this is L. So that this doesn't know because L just comes out of here. So my momentum conservation, this is P1, and this is P1 L. So this thing is just going to look like 2P1.L. But then each one of these diagrams, these propagators will be different, okay? Because one has momentum L coming in, and the other one has momentum Q minus L. So this is going to be 2P2.L plus I epsilon. So now I'm going to keep track of the I epsilons carefully of the integral, because you'll see that will be important. And then the cross box, I have the same thing, but now I have 2P2 dot Q minus L. Okay, so let's keep going. But now I told you that P2.Q scales like Q squared, which is smaller than P2.L. P2.L just scales like Q. Okay, so what does this look like? This combination here, when I expand it, so this is simply 2 pi I times delta P2.L. Okay, I'm using this magic distributional identity, 1 over x minus I epsilon minus 1 over x plus I epsilon equals 2 pi I delta of x. Okay, so we see that if we add these two integrals, we're just cutting this linear propagator here. But now let me take the result and then just average over the two possible ways of labeling. So here I chose L to be here, and I'm going to relabel L and then Q minus L. Okay, so let me take the result here and just write this thing. So let me call this plus the same thing that when I take L to Q minus L. So I'm allowed to do that because it's an integral. I can label it any way I want. Right, so the result of this now will be the L of L squared minus Q squared. I had this Q2 dot L. And once again, I'm going to get 2P1 dot L as I epsilon plus 1 over minus 2P1 dot L as I epsilon, which again will be proportional to. Okay, so the result looks like something like this. Okay, so what is this? This is very simple. Let me write it in a specific way. So this is, I have 1 over L squared. Okay, I have this measure, P1 dot L, P2 dot L, and then 1 over L squared times 1 over Q minus L squared. But this is a convolution. This is a convolution of this tree-level diagram convolved with the tree-level diagram. And we know that the Fourier transform takes a convolution into a product. Okay, so even without knowing the scaling, just by being careful with this I epsilon, we would have seen that this amplitude in momentum space is a convolution of tree level with itself, of this Born amplitude, right? So let me just write it here. The Fourier transform of this thing, sorry, there's a 1/2, importantly, which I shouldn't forget. This is 1/2 of this squared. So what happens more generally? So if I keep going, so here I have these two integrals. At the next order, I will have six different permutations of this kind of double box type of integrals. So this just gives you the Born amplitude. This will give me this convolution with a factor of 2. The combination of all of these amplitudes at the next order, at leading order, will give me 1/3 factorial, the triple convolution. And that's how we see this exponential being built up order by order. Okay. So that's how we see, as I was promising, that we get terms like this square of the leading order or kind of products of lower orders. So in general, this will tell me that it goes like exponential, kind of a convolutional exponential of the Born exchange. And then here there can be subleading corrections. Okay, we can also do this a bit more formally. So here we see that in momentum space, the exponential is a bit funny because it's a convolution. In impact parameter space, it's just a normal exponential as a number. But what we are really seeing here is that formally, in this classical limit, the S matrix exponentiates as an operator, right? So we can take our S matrix, which is something like 1 plus IT, and recognize that in this classical limit, this is not a good parameterization. A better parameterization will be an exponential parameterization, which, well, first of all, it will trivialize unitarity as long as this n is a Hermitian operator. So these are all operators. But now I can invert this relation. So I can write In is log of 1 plus IT. And if I'm going to compute things perturbatively, I can just expand this log. So a leading order, we see that these two things are the same, but then there's going to be corrections. So this will be IT times IT. There's going to be a 1/IT cubed. So all of these are statements about the S matrix as an operator. And in order to evaluate a matrix element, we'll need to insert a complete set of states. Okay, so for instance, if I want the matrix element of n with P1, P2 as initial momenta, and P3, P4 as final momenta, okay, so this will just be the same thing of T. But now there will be a correction, which is minus 1/2 of matrix element of IT. But now I have another power of IT. So let me insert here a complete set of states. So this can be anything which is crossing the cut. So let's draw a picture that conveys the same thing. So what is this n matrix element that computes the phase of this matrix? This object n will just be the original amplitude. But now I need to subtract minus 1/2 of some cut, where I can have anything else crossing the cut, plus dot, dot, dot. Okay, so that's what it means to take the logarithm of the amplitude to extract this classical quantity. Okay, and at one loop, this will be very simple. So at one loop, what is this? Okay, let me just erase, but if I just care about this at one loop, then there will be the one loop amplitude, and here, okay, if there's something else apart from the two particles crossing the cut, that will be higher loop. So I just have to subtract the square of the tree. And what is this object? This object is just the L. So let's say that the momentum transfer here is L. The momentum transfer here is Q minus L, so that the total momentum transfer, remember this is Q. And here I have the full on-shell condition, so L plus L squared. But then when we expand in the soft limit, I can just forget about these L squared corrections here, and then we get back precisely what we had here. So we see that if we take the logarithm, then this two-particle cut will precisely cancel this term that we got just from expanding the amplitude. So here, there's a cross and a cross box, a box and a cross box, and then when I subtract this two-particle cut, it will just cancel, which tells me that we're really computing the exponent now, and we are subtracting just the square of the tree.
Discarded the X contributions, I guess, from more gravitons, because that will be amount to some quantum correction to this.
You mean higher loops, or?
Yeah, here the sum over X. In the end, I think here we just went back to exchanging the ladder gravitons.
Here, the only thing that we discarded is extra states crossing, because I'm focusing on the one loop amplitude now. So I just wanted to look at like which diagrams I could, if for instance, something that would contribute to this diagram with some extra particle here could be this H diagram that we looked at yesterday. But this is always going to be higher loops. Okay, so the only reason why I threw it away is because I'm focusing on the one loop amplitude. Indeed, if you go to the two loop amplitude, you need to worry about this. So you need to include these extra states to take the logarithm properly. So you will need to subtract the imaginary part of these graphs to really compute this phase appropriately. Yeah, it's just it's necessary because here I just define the n as an operator, and to compute it, I need to include all possible states. No, this will actually be classical. Yeah, quantum will be, there will be other diagrams which are quantum. So for instance, earlier we were worried about this diagram that looked like this, right? There will be a cross version of this, right, where I just have something like this. And then by the same principle that I showed here, that when I take the logarithm, the box cancels against some cut, then there will be a term here where I will have the tree amplitude and the one loop correction, quantum correction to the one loop amplitude that will cancel when I add with this thing. Okay, so you can see that when you take the log, all of these corrections that we were worrying about, which naively had classical counting, they will cancel in the logarithm. But at tree level, at one loop, the quantum corrections are inside of the same diagrams that give classical corrections, with the exception of that bubble of gravitons. Yeah. Yes?
So I was under the impression that the exponentiation you were talking about was the exponentiation of t. So like actually this was
Yeah.
we write this as s is equal to in, then we're assuming t is small, but gravity level amplitude is not small. So how is that expansion even like justified log of 1 plus I? Because t in principle is not.
Well, yes, I mean, this is a formal power series expansion, right? So we are precisely trying to solve that problem, the problem that t is large and n is the thing that we are after, right? So yeah, indeed, this is a formal power series expansion, but the point is that in each individual term, you would have things that grow too fast, so the series wouldn't be well-defined, but they cancel so that you get n, which now is well-defined.
So it's something that just works out when you put it in practice, essentially.
Yes.
But like, is there a reason why you can see so maybe this connects with the previous question? The higher loops, we know that these cancellations are always, as far as we're interested in classical results, is there a way to like show that this is true, or it's something that works?
So, well, it's something that we know how to do at some order, but I don't think there's a proof to all orders, but it would be very surprising if it doesn't work. Yeah. So for instance, we can do these ladders to all orders in perturbation theory and just show explicitly that they exponentiate or that they would cancel with the logarithm. But then the combinatorics gets complicated because then I have like 1 p.m. times 2 p.m., any combination, right? So if you have a perturbative expansion of the exponent and you expand that now, then the combinatorics gets pretty complicated. Yeah. Okay, more questions.
Is there any condition of x? So x is any set of all the possible intermediate states, or would we like constrain it as well?
No, the only constraint is that because we're taking this classical limit, then we have to have these two particles because we cannot annihilate them. You can convince yourself also that you couldn't have, by the same principle, you couldn't have an extra pair of massive particles in the intermediate state. Okay, that would be some quantum process. So maybe as a little exercise, think, for instance, why this kind of annihilation process would be suppressed, or like pair creation process would be suppressed in the classical limit, right? So typically what this is going to look like is these two particles plus a bunch of gravitons. And how many gravitons you have depends on how many loops you have. Okay, more questions? Okay, so hopefully this has convinced you of this whole business that the S matrix is exponentiating, which is a bit annoying because we need to kind of find which piece inside of it is the one that we're interested in. But at the end of the day, all is good because we can either take the log formally and write this in terms of amplitudes under unitarity cuts, or just compute at each order and see that we get convolutions, and then we just throw away those pieces and then focus on the one that we are really interested in. Okay, so in practice, what we do is we have some diagram, we just expand to the order that we believe that there's something classical, and then we focus on that order, and then just assume that the other ones will work out, which you can, of course, show case by case. Yes? Yes, indeed. So this is a general statement that we expect to be true for classical in this classical limit. So you can actually try to write a specific formula for this n as an operator, and what you will see is, okay, here we had like a 4-point part. So this would look like this phase of the S matrix, which was, okay, for instance, in momentum space, it was just a number. It was just this true level amplitude Fourier transform, right? Times kind of creation annihilation operators that tell you that I have two particles in the in state, I have two particles in the out state. But there can be a correction that will look like the 5-point amplitude. So you can also have an extra graviton in the final state. So you can expand this operator in the number of particles, just like you would do some operator that can create annihilated particles, and to compute at each order in the radiation what happens. And So people have proposed that you can stop at the leading order, that if you just have 5 particles that captures all the radiation effects that we want in classical GR. But I think now there's some evidence that this is probably not correct, because we know that gravity is nonlinear, so there can be kind of nonlinear interactions between the radiation, which this kind of coherent ansatz probably doesn't capture. Yes. Yeah.
Basically, the same question, what happens at 5 higher points? But basically, if you have radiation, then it's like an imaginary contribution to N, or
so in the 4-point amplitude, radiation has multiple effects. So first of all, the first real effect with radiation starts at 2 loops. So we won't have time to discuss because it's more complicated, which is precisely when you can have a non-shell graviton crossing this cut. We'll see later why at 1 loop this cannot happen when we look at the velocity counting. But yeah, so here it will show up first as an imaginary part in the 2-loop amplitude or in the 2-loop phase. However, by analyticity, that has to come with a corresponding real part. So it's not only in the imaginary part; it's all over the place. So there's a contribution to so-called radiation reaction contribution to the real part of the amplitude that tells you that you can have kind of radiation that tries to leave the system, but then actually affects the motion of the particles itself. Yes. Yeah. Okay, this is kind of beyond. So for most people, this doesn't make sense because you're not experts. Don't worry. But this picture that here I'm illustrating with this 4-point amplitude, it's much more general, and of course you can look at higher point amplitudes too. Okay. More questions? Okay, so before we leave this story of exponentiation, I just wanted to comment on what is actually this phase that we are computing. Because I'm telling you it's some classical object, but what is it? Okay. Is there any guess? Does anybody want to guess what the log of the amplitude actually is? And I see some people smiling, which probably means they already know, so you cannot answer. So guess? Okay, so it's actually something very familiar. If you ever thought about the semi-classical expansion, only slightly different, because typically, okay, so what is the textbook story about the semi-classical expansion? We have some path integral, right? Some time evolution that we compute via path integral. Same here, it's just the S matrix. We're computing the time evolution from -infinity to +infinity, but still time evolution. So for instance, the Feynman path integral can compute the matrix element from some initial time to some final time for a particle to go from some position to another, right? So we have some amplitude for some particle to go from here along some path, Q initial, Q final. And how do we compute this? We compute it as the path integral. So let me write in the Hamiltonian formalism, F Q and P, with initial, P initial equals Q initial, with boundary conditions for Q fixed. And I have the action, which is a function of this path. Okay, and typically what we do is we say, okay, let's just compute this by expanding around the classical path. So we say that Q is Q classical plus some deviation, and P is P classical plus some deviation, right? And okay, so this action here is just the usual thing. It's going to be P dq minus H dt. So H depends on P and Q. So if I expand around this path, what am I going to get? I'm going to get delta P, then so if this is a solution to the classical equation of motion, these are just the Hamilton equations. So this is just 0 when evaluated on this classical path, right? And then, importantly, there's also a boundary term, which is like P delta Q, but this is evaluated at T initial and T final, but we fixed the positions at the beginning, at the end, which means that this delta Q needs to go to 0. So this also goes to 0, right? And of course, I forgot, but the leading term was just this thing evaluated in the classical path. Okay. So the usual semi-classical approximation just computes this path integral. So this probability amplitude as the exponential of the usual action, right? So what we find is that this Q final, Q initial, T initial, at leading order is going to be e to the I, this classical thing, and then there's order h bar corrections, so things which are quadratic in these fluctuations, but the fact that there was no linear term tells us that this is a pretty good approximation. Okay, this is almost what the amplitude is, with a slight difference, right? So when we compute the scattering amplitude, we don't fix times and positions. Okay? So what we fix are momenta and energies. Okay? And notice that, for instance, if I fix the momentum and not the position, then this boundary term is not under control. Okay? So what the amplitude is actually, or the S matrix element, so 1 is IA, it's P final, E final, E initial, E initial. So now we need to think about this path integral. So this is almost the same, except we need to add appropriate boundary terms to this I to make sure that the variations will work out. So there's another object, which is S of Q and P. So what is this? This is the original I of Q and P. But now I need to add the right boundary terms, which is just PQ evaluated at P final, Q final. Actually, let me write it as a total derivative. So this will be Q minus ET. Okay, so this is just a boundary term, but notice that because I'm adding this thing here, when I do the variations, this will switch this boundary term to, instead of P dQ, to Q dP when I do the variations. So the variation of this boundary term would cancel precisely this and leave me something that, if I leave the momenta fixed, actually cancels out. Okay, and similarly, if you do the path integral where you're fixing energies, not times, you need to be careful. So this was from kind of T initial to T final. But if you fix the energy, you actually need to vary the endpoints too. And the second piece will cancel the variation of the endpoints. Okay. So this is actually something pretty simple. And then this object here that we have, the amplitude, will be the exponential of this thing evaluated in the classical solutions. Yeah, the role is that when we do a path integral with fixed energies instead of fixed times, you need to allow variations of the final and initial time of the process because you don't know when the thing finishes. Okay, so that will also generate some piece that goes like delta t h coming from this term here at the final time, or delta t h at the initial time, which are canceled by this boundary term. Okay, so you can play with it and see that this actually plays the right role. But yeah, that's what it does. So this is maybe more unfamiliar. Maybe you haven't seen these path integrals with fixed energy and momentum, but this is how it works. It's just adding the right boundary terms so that the variational problem is well defined. And actually, this is what we are computing. When we are computing this log of the S matrix, is something like this. It's just the kind of semi-classical on-shell action with fixed, and trajectories that have fixed momentas and energies. This is not a dot. This is something that I didn't erase. Yeah, just PQ. Yeah. And for instance, if you take a two-body system, which is mediated, whose interactions are mediated by central forces, like the two-body problem, then you can just check that this corresponds to something that people call the radial action for the dynamics. So these boundary terms are important because they will cancel a bunch of stuff in the semi-classical on-shell action, and they will just leave one interesting term, which is called the radial action integral, which is just the integral of the radial momenta along the trajectory. Okay, and this is, okay, if some of you have been keeping track of the literature, this is what people usually compute. Okay, any questions about this whole story? This is everything I have to say about this exponentiation, how the classical phase is related to the amplitude and what it is. And now we're going to switch to counting masses and velocities. Yeah. I mean, you can always compute the phase of the S matrix by taking this logarithm, right? And so that's always well defined. Whether it has some nice interpretation, then it relies on this large angular momentum. So of course, there's always like the phase shift for 4-point scattering, which you can compute, which depends on angular momentum and the energy, and that quantity is always well defined. But here it actually has some nice physical interpretation as the on-shell action for some process, but that only works in this kind of large angular momentum or kind of small impact, small momentum transfer limit. Okay, the mass counting is a whole other topic, so maybe I can give you 2 more minutes to ask questions before we take a break. Yes? Okay, good question. So the question is basically, what is the correction that I haven't written? Right, so when I take the amplitude, or 1 plus I times the amplitude, and I write as an exponential, okay, the leading term was this Born amplitude, right? The correction, well, in 4 dimensions, just comes from these triangle diagrams. The box fully cancels. That's an accident of 4 dimensions. So the subleading term in the box just happens to be 0 in 4 dimensions, but in general dimensions it's not. So in general dimension, there's going to be also some correction that looks like kind of this thing at subleading order. Okay. And indeed, when you go to high orders, generically, every single diagram contributes at some order in the expansion. So it's only in 4 dimensions that there's something special. So for instance, there was a At some point in time, people believe that only diagrams with triangles could contribute classically. That is not correct. That's an accident of one loop in 4 dimensions, right? But yeah, more generally, you would expect that any given diagram, if you expand at the right order in Q, it might contribute unless it has something like a loop of gravitons or something which clearly will be quantum. This one, it does, but at the next, so if you go to 2 loops, everything will contribute except this one that I was promising you that will cancel. So this one won't contribute, but everything like this H diagram, you can have diagrams that look like this, which we'll discuss in some detail in a second. You can have some subleading term in the expansion of this box. So remember, at the beginning, we said that at the subleading order of this, there would be something that looks classical, that contributes. So yeah, essentially everything contributes. Mm-hmm. This one? No, this always cancels. It always cancels when you take the logarithm, because this is really the product of a quantum correction and a classical thing, which in the amplitude, it just looks like classical. There's h bar over h bar. But when you take the logarithm, then you can disentangle those contributions. Chrissy. That's right. In principle, there's also a series of quantum corrections which are still long distance. So as I mentioned, they're still calculable. We could compute them. So for instance, people have computed at the leading order in the small velocity limit what the leading quantum correction is. So it's a result about 20 years ago by Donahue. Well, maybe he did it even 30 years ago, but it was revisited 20 years ago. Donahue, Bierumbohr, and friends. But for instance, no one has computed what the all orders in velocity leading correction to quantum to the Newton's potential is, or to the scattering angle, as far as I know, which would be the kind of leading quantum correction to this, which is keeping the quantum term in every single diagram. Okay. Okay, so maybe we can stop here for a break. When do we meet again?
In half an hour.
Half an hour. Okay, great. Thanks.
Let's resume at 3:30.
I'm already saying that is the cut diagram will take care of the exponent.
So the cut diagram, what it does, it cancels the, so this H diagram will have a real part and an imaginary part.
Yeah.
When you take the logarithm, this thing will cancel the imaginary part of this diagram.
Which machine will cancel?
This cut.